Hello everyone, it's a pleasure to be here to present our work, Unified Gesture, a unified gesture synthesis module for multiple skeletons. I represent the following 5 aspects. First, the background. Current gesture synthesis modules are designed for specific skeletons, making them less versatile. These models struggle to generate across different skeleton structures, leading to inconsistencies in gesture generation. With the increasing variety of skeleton data sources, there is a promising need for a model that can handle multiple skeletons seamlessly. A unified approach would ensure consistent and accurate gesture synthesis, irrespective of the skeleton structure. To develop a robust and versatile unified gesture synthesis module that can effectively handle multiple skeletons. Aim is to overcome the limitation of existing models and set a new standard of the field of gesture generation. We employed a skeleton-aware retargeting network to unify the different skeletons to a common from skeletons. We are extending the dataset. To present a time-aware, attention-based diffusion model on the primary skeleton for speech-driven quasi gesture generation. By virtue of the diffusion model, we can deter the style of the gesture, setting the initial gestures and generating diverse gestures. We introduce reinforced learning with a learned reward function to refine the generation model and make the model explore the data. The explorer space for reinforced learning is reduced by learning a codebook with VQVE to summarize meaningful gesture units. Extensive experiments show that our model can generate a human-like speech matched, stylized, diverse, controllable, and physically plausible gestures that significantly outperform existing gesture generation methods. Next is the method. Here is the gesture generation path of our proposed framework. We retargeted the different skeletons to the primer skeleton. Given a speech segment, optional style says gesture, the output is the primer gesture after VQA encoding of the output of the diffusion model. We introduced reinforced learning to refine the gesture generation network. Finally, gesture of the skeleton is specified and generated with physical guidance. We use graphs to represent motions. Selectivity is determined by the kinematical chance. Nodes to represent corresponding joint ends, and in particular left node to represent the NF. We take 2 datasets A and B as example. We first need to set the position and the rotation of the unified reference poses, such as T-pose or pose. We first centralize the reference representation to the root joint. For example, the talking with hand dataset uses the word joint to maintain head. 2 reference poses can be aligned through global and local translation and rotation. To unify the motion of the different screens, we use a retargeting network. Here we take state component and the dynamic component of skeleton A as an example. First, we adapt the skeleton convolution and pooling layers in encoders to extract a deep latent representation of the motion, where operator repeats below scales and concatenate along the time dimension. Assuming that all skeletons contain 5 and effect 2 hands, 2 feet, and head, and 2 middle lobes. We use the latent representation of the primal skeleton to represent all the different skeletons, which contains only 7 nodes. Loss of the retargeting network can be computed. For details on the network structure, please refer to our paper. We unified the gestures by retargeting the skeletons of different gesture datasets to a primary skeleton and now a beaten multi-deep primal skeleton gesture set with the corresponding speech set. to generate the cold-speech gesture with a diffusion model, we introduced diffuse style gesture, which has recently achieved stronger results on a single dataset as our backbone, as shown in Fetcher. The diffusion model consists of two parts: the forward process, diffusion process, and the reverse process, deloading process. We denote the generated gesture as R in the diffusion process, which has the same dimension as an observation data. Our goal is to synthesize a gesture given Lloyd stacks, Lloyd gesture, and conditions, including audio, dial, and state gesture. Audio features are generated from the Bertrand model of WaveLM. Random masks are added to the pipeline of the seed gesture and the style gesture processing for classify-free learning. The deloading module can be trained by optimizing the Hilbert loss. The final cold-speech gesture is given by placing a number of ellipses of time duration with frame length. For every clip, in every Lloyd step, we product the clean gesture and add the Lloyd to the next Lloyd step with the diffuse test. This process is repeated from TD until 0 is reached. This refers to our paper for training details such as network structure and implementation. Here we train a VQVE to summarize meaningful gesture units to reduce the exploration space for following reinforced learning. Each code represents a unique gesture. Besides, discrete spaces are more conducive to reinforced learning for exploration. The architecture of the prime gesture VQV is shown in figure. Given the prime gesture sequence of the upper body, we first adapt a 1D temporary convolution network to encode the sequence to context-aware features. Then we quantize them by mapping each temporary feature to its closest codebook element. Following the convolutional decoder projects them back to the deep latent space as a prime gesture sequence for the upper body. To further enhance the alignment with the speech and gestures and increase the diversity of the generated gestures, we employ the reinforced learning to refine the gesture-generated module. The reward signal is the pivotal imbalance in exploration in reinforced learning. We adopt inverse reinforced learning to learn a neural network module from human demonstration to fit the true reward function and explanation human behavior. Specifically, our reward module training is shown in figure. Firstly, we sample a speech pair from the VQA coded dataset, denoted as a trajectory. Then we randomly replace codes in the trajectory to generate other trajectories. We sample tuples and thus get trajectories to form new datasets to train the reward model. We make a weak perception that the more codes replaced with random codes, the worse the quality of the trajectories, including alignment with the speech and diversity. There, we let the reward model classify these trajectories with different quality, may come from different human demonstrations with different speech, to determine which trajectory is better. By learning the classification task, the reward model can learn to output a scalar reward signal that makes reasonable evaluation on the quality of the trajectory. Given the reward model, we use the reinforced algorithm to improve the model. We consider that the foot should have contact with the ground when there is a left-right acceleration or an upward acceleration of the root. Then we use standard inverse kinematical optimization for physical guidance. For more details, please refer to our paper. Then comes the experiments. We perform the training and evaluation of the change and react datasets. Even based on motion capture, the hand quality is still low, so we ignore hand motion currently. when the number of joins for two datasets is 26 and 27 respectively. We chose 7 more typical and longer duration styles: happy, sad, neutral, old, relaxed, angry, and still for training and evaluation. For the Trinity datasets, there are no style labels, and we consider all of its styles to be neutral. And we divided the data into A2121 by training, validation, and testing. We compare our proposed model with style gestures, audio to gesture, example gestures, and diffuse style gesture. The quantitative results are shown in table. On the global CCA, our proposal outperforms all other existing methods. Hence, the global CCA shows a stronger clumping between the generated gestures and the truth gestures. CCA for each sequence is not as good as the other methods, and we suggest that this is because for each sequence, the model learns the gestures across the skeleton. Our module significantly surpass the compiled state-of-the-art method with FGD. This is show that the high quality of the generated gestures. We can see that our module is not as good as style gesture in terms of diversity. The video result shows that style gesture has a lot of clusters. Increasing diversity will decreasing human likeness and appropriateness. To understand the real visual performance of our method, we conduct a user study among the gesture sequence generated by each compiled model and the ground truth motion capture data. Following the evaluation in Genia, we evaluate human likeness and gesture speech appropriateness. The length of the evaluated clubs ranged from 22 to 50 seconds, with an average length of 35.4 seconds. The mean option scores on human likeness and appropriateness are reported in the last two columns in table. In terms of human likeness, our model significantly surpasses the compared state-of-the-art method. However, it's not significantly different from example gestures. This is because example gestures use a reference gesture as input, storing inference, with already a priori knowledge of the gesture, stemming from a gesture distribution to get the generated gesture. So the human likeness is stronger. For gesture and speech appropriateness, our model significantly outperforms style gestures, audio to gesture, and example gesture, giving competitive results with diffuse style gesture. Moreover, we conduct emulation studies to address the performance effects of different components in the framework. We performed the experiments on following components: reinforced learning, VQAE, and multiple skeletons. The results of our emulation studies are summarized in table. The metrics of FGD indicate that after reinforced learning fine-tuning, the generated gesture have increased the distance from the distribution of human gestures in the dataset, including that the model has explored some gestures that do not belong to the existing distribution of gestures in the dataset, but are considered reasonable by the reward model. From the CCA and the diversity metric, it can be seen that the reward model can indeed generate two gestures outside the dataset, allowing the model to generate more diverse and high-quality gesture movements that are not limited to the dataset. When neither reinforced learning or VQAE is used, both FGD and diversity are still decreasing, which indicates the necessity of codebooks to generate meaningful gestures. When we use only a single dataset, we notice that both FGD and decrease a lot, which indicates the essential importance of gesture generation for learning on multiple datasets. Similarly, we conduct a user study of emulation studies. The modes on human likeness and appropriateness are shown in the last two columns in table. In terms of human similarity, we can find that the scale of the dataset has a significant effect on the result, which demonstrates the importance of unifying the gesture dataset. For speech and gesture appropriateness, it's also found that the scale of the dataset has the largest impact on the metric. Secondly, the appropriateness also decreased without reinforced learning, shows the importance of the data exploration. We randomly select a 2.67-second generated gesture clip when controlling the style and setting noise in diffusion model to generate diverse gestures. The dashed box indicates control they are called the same. For the same speech, different styles of gestures can be generated where pursuing matching with the speech. So to the diffusion model architect, different noise gesture and different state gesture could generate different gestures even for the same speech and style as shown in figure. This is the same as real human speech, which creates diverse core speech gestures related to the initial position. Since we use VQAE to generate the gesture, it's easy to control the gesture or take out the code for interpretation. We can have a high level of control over speech-driven gesture at any time with the specific up-body code as shown in the dashed box. Watch the demo video demonstration here.
But the whole thing is because like that wouldn't work as like a horror experience in of itself, but that whole thing is meant to just get your jitters up, so you're all just like, yeah, kind of like a little bit nervous. And then you get into the next place and you've got like actors doing slightly more complicated roles where they're actually like coming up to you and talking to you and then like leading you down one way, and then something will pop out of the side and you're just like, Jesus. But like this whole thing, it becomes so much more creepy. It's really, really cool just the way.
In this paper, we assume that the body gestures of the different scantons are contained in the primal scanton and present a unified gesture synthesis module for multiple scantons. Unified gesture demonstrates three major strengths. First, benefit from using the scanton-aware retargeting network to unify the different scantons. We are extending the dataset. The model has stronger generalization, and application experiments on a single scanton effectively demonstrated that a large amount of the data can improve the performance of the model. Based on a diffusion model, probabilistic mapping enhances diversity will enable generalization of high-quality, speech-matched, and style control gestures. VQVE learns a codebook to summarize meaningful gestures units to improve controllability and interpretability. Reinforcement learning with a learn reward function helps to refine the gesture generation model, enabling the model to explore the data and able to increase the diversity of the generated gesture. The physics-based kinematical construct also further improve gesture generation. There is room for improvement in this research. Besides speech, more modalities, for example, text, physical experimentation could take into consideration to generate more broad gestures. Solving problem that the skeleton-aware encoder and decoder need to be retrained for the new skeleton is also our future research direction. Thanks for watching.